All right. Good morning, good afternoon, good evening, good night to everyone here. Right? Thank you for taking the time to watch this lecture, which will be about material structure. So, this is to me, right? I'm still Godwin, and we are going to the second part of your MATEPRO subject, right? Just like what we've said before, right? This subject is actually two that were squished into one. So ngayon pupunta na tayo sa materials section, right? More material science section. So these things, right? So things are gonna get a bit more technical. Not that they weren't before, but a different kind of technical. So ngayon meron na tayong medyo may chemistry, so you're gonna have to think about not only bonds but also just how things are going to move. So a little bit of mechanics afterwards. But let's begin, right? I think now that you might ask yourselves is that like why this? Like why me? I'm an industrial engineer. I'm more concerned with the bird's eye view of things, right? But you guys answered this question before with manufacturing. Like technically you are not supposed to be like directly responsible for manufacturing. And now you're also not directly responsible for materials, right? That's for materials engineers. I think kind of that's also within our field, within the mechanical engineering field. So why study materials now? It's because, well, I don't think it would be very outrageous to say that the physical world, in essence, is a world made up of materials, right? Everything is made up of something, and even more so, right? The modern world is only kept alive, it's only kept running because we have so many materials and we have so many things that we can do with them, so many ways we can combine them. And now that we are in a complicated world with complicated materials, studying material science is a way for us to understand what things are made of and maybe ask ourselves if that's why they are used in the way that they are. And an extension of that would be, is that really the correct way? Is that really the correct material for the correct application? Right? Just like before, of course, we need to quote someone to start things off. The scientist describes what is, but for us, the engineer creates what never was. Right? Very material sciencey. This is from Theodore von Karman. You might know him if you're a bit interested in aerospace or basta aeronautics in general. So, let's begin with a preface. I think this is supposed to be section 0, but okay, right? Just a brief preface. And babalik tayo, we're going to go once again into the history of things, right? I hope you would agree with this claim that the state of a civilization depends on the materials that it uses, right? Balik tayo ng topic 1 natin, right? The Stone Age, right? It is defined by people or basta the use of stone and wood tools, right? And by then, it was a simple time. These are the only resources that you have available. And then once they unlock, I don't know, things like, practices like the addition of fire, now you're starting to see, oh, okay, maybe, right, you can use better and better materials. The Bronze Age, right, they realized they could smelt bronze, right, from copper and tin. And now they can use these metals, right, to create or craft better materials for whatever it is they need. And better comes better, right? Iron is lighter, it's stronger, right? And the thing now is that our civilization, right, springs up from the use of these iron tools. Right? So hopefully, the claim follows that the emergence of different manufacturing techniques makes for better materials, which makes for a better, more technologically equipped civilization, right? And now, right? Hopefully, we are in a mutual understanding that yes, manufacturing matters, but it's not the only thing that matters. Honestly, if I were to arrange things, right? If I were to arrange how this course would have been discussed, dapat nga una ang materials, right? If you guys have noticed in topics 1, 2, 3, a lot of the context depends on you guys having some materials knowledge, right? So dapat nga inuna kayong material science, no? But still, it's somewhat manageable naman, right? And in here, right, you basically, for any application, you select the material and then you decide how it's manufactured, because those are the two things that matter. What do they mean matter? As in, those are what will determine the properties and the performance of any material, right? Material plus manufacturing equals properties and performance. If you have a bad material, you manufacture it well, it's still gonna have bad properties, maybe bad performance. If anything, right? If you have a good material but you manufacture it very poorly, what's going to happen is that the good properties sana will be reduced, right? Will be I don't know, botched is a good word to say. And in the modern world, it's no longer just materials plus manufacturing equals properties and performance. It's now also a kind of a modern world where you have to also balance it, have its trade-offs with associated costs, right? You can make everything out of diamonds, or you can make everything out of, I don't know, platinum, titanium, or whatever, the strongest steels you have. Pero how much will it cost, right? Is there even a supply of it on Earth? So ganang klaseng bagay, right? So now, yes, dito na talaga tayo magsa-start, right? A recap on chemistry. And of course, the thesis statement of this is that the performance, the properties of a material depend on its structure, right? Its material structure. And the thing about this is that we will continue this next topic for your last topic, right? Yung properties, it will depend pa on how small you're looking at, right? If you're just looking at the macro, if you're looking at the product as a whole, for example, the shape of, I don't know, a beam or a column or whatever determines the properties. If it's just a ball, right, compared to like something that is long and is drawn out to a wire, of course, it has different mechanical properties. But then if you start looking smaller and smaller, you will see that different arrangements, sabihin na lang natin, right, in these structural levels determine other variations, other flavors of properties, right? For us, siguro, ang importante lang talaga is the mechanical properties, because we're not like, I don't know, we're not chemical engineers, we're not depending on I don't know, like things about how well a fuel will burn, chemical properties, how much fission energy gets out of a reaction. That's for like nuclear engineers, right? Electrical conductivity kind of matters to us sometimes if we're dealing with metals that are used for, I don't know, conduction, but that's for electrical engineers, right? For us, we just want things not to crumble or fall apart, right? And, right, now, I will reveal to you the family tree of materials, right? We're not going to delve in much deeply on all four of these. If anything, it's just one of the four, right? And put your guesses in now, I guess, or something like that. Right? Put your guesses in what these four are, right? Sometimes they are classified as five, pero four excuse me, is what we normally use in manufacturing. These are metals, polymers, ceramics, and composites or composites. Composites is how I like to pronounce. And even then, right, syempre dahil family tree ito, it's not just them, right? They also have their own sons, offspring, bilang natin, right? For metals, there are the different kinds of metals, right? You can mix metals together, create alloys. We'll talk about that later, right? For polymers, it depends, like what kind of plastic are you talking about? Or is it setting, thermoplastic? We've tackled this in our basic manufacturing processes lesson. Elastomers, very fancy way for saying rubber, rubbery things. And ceramics, glass, right? Ceramic porcelains, right? Nanomaterials, as in carbon nanotubes, right? Ceramics. And composites. Oh, actually, ceramics should also be concrete, right? Concrete should also be a ceramic. And composites are the weird ones, are the engineered ones talaga, right? They really changed the internal structure of these materials so that they can achieve wildly different properties, right? Metamaterials, if you've heard of them, laminates, right, where you put two things and then stick them together, and then the ocean gate, if you guys remember that whole issue, the thing why the submarine failed, as based on a lot of people, is delamination, as in like the layers are coming apart, so things like that, right? Pero in this case, I'll just be giving you a surface level kind of thing, just so you are oriented at the very least. Now, how should I think about materials? Okay. All right. And we really are going to go into chemistry for this one. And this is an observation. I don't want to say it's a finding, but everything is made out of atoms, right? And all atoms are made of the same subatomic stuff: protons, neutrons, electrons. We won't go any further than that, right? And of course, atom, right? Atomos, indivisible. It's just the basic unit of everything, right? There's a certain number of protons, neutrons, and electrons, and not much else, right? As you can see, each proton, neutron, and electron are really small, right? The masses of them are contained here, right? MP, Mn, and dapat Me into. Excuse me. Right, but still, right, you can see 10 raised to negative 27 kilograms. Those are tiny, tiny things, right? You can also see the charges of them. You can see that the charge of the proton and the electron are identical, but they are positive for electron and positive for proton, negative for electron, right? And you guys know what these things are, hopefully, right? Positive charges for protons, and the number of protons determines the atom's element, right? The atomic number of something is how many protons it has. And that determines the element of the atom, and at that also, right, determines the atom's properties, right? For neutrons naman, no charges, and the protons and the neutrons are in the nucleus, while the electrons are going to be just floating around, swirling around in there. Excuse me. As you can see here, right? Bam. Right? I'm not going to present the older models. Ito na lang tayo para modern talaga. No more like yung rings around things, right? You will have a very small, very, very small nucleus in the middle of everything with the protons and the neutrons, while there's just an electron cloud, right? Why is it a cloud? Akala ko ba electrons are like discrete things? It's a cloud because, well, I never really know where the electron is. It's just that the denser the cloud, the more probable that the electron is there, right? I should also be using my pen at this moment, right? Maybe it's here, but more specifically, there are lots of electrons that are probably somewhere near the middle, something like that, right? And if you guys are trying to remember, meron nga tayong mga shells and subshells and things like that. We'll talk about that shortly. And ito na nga, right? The thing about electrons is that I think, right, and you would also agree that the amount of electrons, or basically the charge of an atom, is vital in determining their properties, right? And dito na nga tayo, pupunta na tayong shells, right? If you remember looking up at a periodic table, right, you will have S, P, D, and F shells, right? And basically, shells are arrangements of electrons around the nucleus. I won't go any further than that here. Kasi nga, hindi naman talaga to chemistry lesson. It's more just, this is the context that we need in case that you guys have forgotten, right? and the thing about this is that there is a kind of a rule. This is what we call the octet rule. Atoms are most stable when the electron shells and subshells are completely filled. Where is the octet? There's an asterisk here which basically says that if the shells are getting bigger and bigger, there's relative stability with 8 electrons. Kaya tayo octet rule. Okay? Pero The question now would be, okay, what if they don't have all 8? Or what if the shells and subshells are not completely filled? What will happen then? Right? How can they become stable? The question is, they're going to bond with other atoms, right? And this is how we have materials, right? Ito na tayo. Bonding na ngayon. Now, the thing is, the electron structure of the atom determines the bonding that it will probably do with other, it will have with other atoms present, right? And the more significant bond that we have currently is the primary bond. You guys know probably the 3 different kinds of primary bonds available, but this is basically a bond between 2 atoms in one molecule, right? Basta between atoms ang primary bond, right? It is ionic, covalent, or metallic. Let's start first with, ayan pa pala. How can we know which primary bond will occur, right? Depende na. How will atoms know, you know what, I'm gonna make an ionic bond with this guy? And it will depend based on a concept known as electronegativity, right? Electronegativity basically is a degree of how much an atom wants to gain electrons. Negativity, right? Which means it wants to become more negative. How do you become more negative? You get more negative charges, aka you want to gain electrons, right? If something has a high electronegativity, it wants to take, right? It wants to gain electrons for itself. Kukuha siya. But if it has low electronegativity or electropositivity, gusto niya maging electropositive. So it wants to give away electrons. Right? So hopefully that makes sense. And now, ito, oh my gosh, babalik tayong periodic table for this one, right? Periodic table, I blacked it out, made it black and white so that it's prettier to look at. There are too many colors here. What we want to just see is how electronegativity is increasing or decreasing in the periodic table. And this is by no means a rule, right? It's just something that chemists see, right? Because eto na nga, right? You might say that going from left to right increases electronegativity, while going up, right, increases electronegativity as well. So you might say, okay, you know what, if I'm going to ask you what is the most electronegative element in here, you would very specifically just say, oh, it's helium, right? Those are what the 2 arrows are pointing to. But you should be cautious because, right, because ideal gases are already stable. And there's a small asterisk. In there because actually, krypton and xenon are quite electronegatives. You might be thinking, wait lang. Ideal gases are ideal, or they are stable because they are at the end of the line. Kumbaga, their electrons are already full. Their shells are already full. So you might say, okay, they're stable, right? But this is why I don't necessarily say that everything is a rule, right? Just because I've told you that going left to right or going bottom to up means that you increase electronegativity doesn't mean that that is the case, period, right? There are lots of exceptions because, you know, we're dealing with chemistry here. There's always going to be an exception, right? Lots of chemistry rules, like let's say for example the Aufbau principle. You don't need to talk about, we don't need to talk about that, but there are lots of exceptions in here because, well, everything is different, right? And in this case, kung ganon, what would be the most electronegative element now? That would mean that fluorine is the most electronegative element. And eto na rin, if I'm going to ask, right? If I'm going to ask which one is the least electronegative element, you would very easily say, kabaliktaran lang ng fluorine. You go left and down, the francium. So it'd be like, okay, yes, it's francium, but it's actually cesium, right? So it's the thing above francium pa talaga, right? So just goes to show how this is not like a be all end all kind of thing, right? Now, ito na tayo, ionic bond. From the word ionic, right? This is a primary bond where you create ions, right? How do you create ions? Ions are basically atoms wherein the charge is not zero, right? If the charge is not zero, ibig sabihin the number of protons and the number of electrons are not the same. Either mas maraming protons, which means mas maraming positive charge, which means positive, or baliktad, right? Pag mas marami electrons, that's negative, right? A positive ion is a cation, and a negative ion is an anion, A-N-I-O-N. And the thing about this is that why are ions being created is that yun nga, they want to create stability. Maybe yung isa nasosobrahan lang ng isang electron, yung isa kulang ng isang electron for them to fill their subshells, their shells, electron shells, edi magbigayan na lang sila. Right? Electrons from one atom are transferred into another. This is only possible when one atom really wants to give away and one atom really wants to take one. Right? So let's say, for example, salt. Right? Very, very common ionic bond example. Here we have sodium. Right? And if you nakita natin ang sodium kanina, sodium is here. Right? If you guys don't remember how to read, right, the periodic table at a glance, ibig sabihin, the first group right here, group 1, I don't even know if it's called group 1. Yeah. Group 1, what happens with them is that they have one valence electron. They have one outermost electron. And so for them, they really want to give that away because if matanggalan sila ng isa, then they're stable, right? The last one, the subshell or the shell behind them is already full. But for something like, I don't know, chlorine, right? They are second to the last. They are missing that one last electron for them to get to the other side, to get to a stable configuration. So what are you going to do? If sodium has one, and then chlorine has one missing, ano gagawin nila? Right? They are going to, right? Sodium is going to give that away and chlorine is going to take it. Because sodium gave it away, natanggalan siya ng negative charge and now it is a net positive charge. And then chlorine got one extra negative charge, which means it's now net negative. Both are now ions and now they are bonded. Okay? And because, right? And because ang nangyayari nga dito is that nagbibigayan sila ng electrons, they are all relatively stable. And if they're relatively stable, that means that these structures right here that you're going to see are going to be strong. Right? But we know the parang the very hindi ko nga alam how to describe that, very human, very observable kind of trade-off. If something is strong, then it's brittle, right? And if it's very weak or soft, then that means it's ductile, right? And because nga these what do you call these things? Ano tawag dito? Right? Because these atoms, they are now stable, right? Their electrons are hard to displace. They are hard to parang jiggle out, right? That means they're also going to be hard to melt. And because nga no electrons are like free to float around, they are now insulators. Right? Wala ka nang makuhang mga extra electrons lying around. They're stuck to everyone. Right? They're stuck to everyone. Okay? And so, punta na tayo sa next nating bond, primary bond. It's covalent bond from the word from the root word ba ito? Basta from the prefix co, which means together, you're sharing valence electrons. You're now sharing them, right? Instead of giving and taking away, you share. This is only possible when there's an electronegative difference that is very low or minsan even identical. So walang difference in electronegativity. If pareho kayong ayaw nyo magbigay or ayaw nyo kumuha, edi mag-share na lang kayo. Right? That's not a form of giving or taking, it's just sharing electrons. Like for example, marami tayong mga diatomic na mga, what do you call this, na mga bond, right? And in a lot of cases, we have, let's say, for example, I don't know, hydrogen gas. So it's hydrogen forming bonds with another hydrogen, oxygen bond, oxygen gas, right? Oxygen gas is double bond. Nitrogen gas is triple bond. In this case, I will just go with chlorine gas, right? Chlorine is still diatomic, Cl2. You might think, okay, wait lang, pareho silang 7. They really want another electron, but where is the extra electron? Where are they going to get that? Well, if you think about it, if you arrange them in such a way where these chlorine atoms are close together, you can arrange the electrons such that if you think about it, each of them now has 8 on their valence shell. If you count, look at this, 8 nandito sa left, 8 din nandito sa right? They are now sharing these 2 electrons. They are making things work. They are making things stable for themselves, right? That is how covalent bonding works, right? And some notes lang about covalent bonding is that the thing is, they don't have to be symmetric, right? Yun nga sinabi natin kanina, maraming diatomic. So O2, N2, H2, Cl2, F2, fluorine gas. I think there is fluorine gas, right? But they don't have to be symmetric, right? You can get hydrochloric acid, hydrobromic acid, lots of different acids are H and then something. Hydrofluoric acid, right? Many things. And they can share more than one pair of electrons. Yun nga sinasabi natin, oxygen gas has a double bond. Nitrogen gas is a triple bond. And the thing about this pa is that because of this arrangement where they're sharing electrons, ang nangyayari is that now there has to be a specific arrangement for these atoms to work, right? You can't have just you can't have just a connection willy-nilly. These sharing configurations need to make sense in the 3D space. So, for example, right here, we have these sharing connections. Let's say, for example, this is a carbon in the middle. A carbon usually has 4 valence electrons. It can share those 4 with 4. It can share those 4 electrons with 4 other substances to create the 4 plus 4. It can create the 8 that it needs for stability. Pero hindi lang pwede yung parang naka-cross lang. If you guys remember from chemistry, kailangan talaga everything has to make sense. Everything needs to be the least amount of energy, ganong klaseng mga bagay. So in this case, we have somewhat of a tetrahedral kind of formation here, right? And because these bonds are a bit more parang a bit more variable, depende na yung magiging electrical properties ng covalent bonds, right? You can either make conductors or you can make insulators or things like that, right? And now, the third one is the metallic bond. It's bonding where bawal ka mag-give or take and then bawal ka ring mag-share. So, the electrons are just, they're just around. Right? This is what happens in the middle, right? As you guys have seen earlier, there's a large chunk of the periodic table wherein it's just in the middle, right? There's a bunch of valence electrons for these guys. Let's say, for example, just metals, right? Iron, copper, things like this, right? And then they bond with themselves. And the thing about this is that okay, they bonded with themselves. Like, let's say, for example, sodium, right? Sodium is a metal. And what happens is that when you're bonding with each other, well, there are these bonds that happen or there are these bonds that occur, but you can see all of them have one extra valence electron. So where are those valence electrons going to go? They're just going to float around, right? There's an electron cloud where electrons freely move. And this is why metals are electrically and thermally conductive. Di ba ang sinasabi natin, what is electricity in the first place? It's the flow of electrons. So, if you have a material which whose bonds enable it to have just like an electron cloud or basta a freely floating sea of electrons that permit movement, edi that's going to be very electrically conductive. Ito another picture from the book. Right? Metallic materials have variable properties based on its configuration. We have seen many different kinds of metals appear here, but we know that these metals are good conductors because nga of the electrons. And the thing about this is that the metallic bonds right here are a bit weak in the sense na hindi naman weak yung material itself, but now it's ductile because these things are now able to bend and stretch and deform and conform, right? Yeah. And now, tapos na tayo sa lahat ng tatlo na primary bonds. We're now going into secondary bonds, or what we would call van der Waals forces. Right? These things are secondary, or these forces are basically secondary bonds. Sabi natin, primary is between atoms, and then secondary bonds is between molecules, right? So the bigger ones. Excuse me. And what happens is that these van der Waals forces are basically operating on opposite charges attract. Right? What do you mean? Opposite charges attract, like ions. Siguro, pwede pa, yes. But what we're talking about here is that when a bond forms, when a molecule forms from different primary bonds, what happens is that sometimes, yes, they are symmetrical, but sometimes they're also given unequal distributions of charge. The most famous example of this would be water, right? Water is made out of these guys, right? 2 hydrogens, 1 oxygen. And what happens is that, medyo spoiler, but they're going to go into covalent bonding, right? Covalent bonding, what do you mean? Pwede namang mangyari is that, well, sabihin na lang natin, the hydrogens give up each of their electrons, right? And then they give it to oxygen, which has somewhat of a high electronegativity. But what happens nga, see, lots of exceptions possible here, right? And I won't go into the details of why it prefers covalent bonding over ionic bonding, but what happens is that they stick together in this configuration. And sayang nga, this is supposed to be 3D, but the best I can do is 2D right now. This is not 90 degrees, right? These the angle here is not 90 degrees. It's like more like 100 something. I think it's 103.5. I'm not sure. You know what? Let's just see. Teka lang. Angle, water, hydrogen. 104, not 103. 104. Close enough, right? Close enough. 104.5. So if you guys are going to remember, I forget what year you are. I think you guys are second years. Balik na lang tayo sa Baschem natin, right? This is the VSEPR, VSEPR model, right? Depending on how many lone pairs you have, depending on how many bonded pairs you have, your molecule will assume different shapes, right? And this is what we call a bent pair, I think, right? And basically, okay, you know what? Let's discard that. Let's just see in here that, look, doon sa taas, we will have many more electrons, right? So in this case, we will develop a kind of a negative charge, a more net negative charge. But for here at the bottom, we're going to see hydrogens, which have, on purpose, a more positive kind of charge, right? And so now, if we place different water molecules in this configuration, let's say, for example, this is just a puddle or a drop of water, what will happen is that unequal, or sabihin na natin opposite charges attract. The negative sides will attract to the positive sides and vice versa. These are your van der Waals forces, right? And this is why lots of fluids have surface tension, right? This is what is responsible for things like surface tension. Okay? Now, ito na tayo sa ating mga claims, right? Now, the atomic structure is not solely responsible for properties, for performance. The arrangement also matters. What do you mean arrangement? Right? We'll talk about this more, but in this case, right, let's suspend that thought for now. And ito na nga, ito yung sasabihin ko sa inyo, yung scope natin is more very clearly on metals, right? Because they are very important to the industry. And I understand that like plastics are also involved, but in this case, let's just narrow our scope down so that this doesn't evolve into another class for you guys, right? Another subject for you. But basically, why am I putting so much focus on metals? It's because once they cool down, once they solidify, they assume a crystalline structure. So you may be wondering, what do you mean crystals? As in like glass? Right? Metals are crystals? Right? So now, pupunta na nga tayo sa structure natin, right? What do you mean structure? As in the arrangement. Siyempre nga structure nga, di ba? And we have three types of molecular or basta atomic structure. They're going to be molecular, crystalline, and amorphous structures in chemistry. In molecular, right? In molecular structures, what we basically mean is that nakikita mo, you can see distinct molecules appear. Like for example, molecules of water or carbon dioxide or blah, 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 right? In here, the molecules are free, right? To do whatever. They are most likely liquids or gases in this case, right? And in this case nga, okay, because they are free to do whatever, ang nangyayari is that they're not very dense and they are very easily turnable into one phase or the other, right? You can, say for example, water, diba? Maliit lang ang phase change temperature niya compared to, I don't know, something like iron, thousands of degrees before it melts, right? And I don't even know what the parang boiling point of iron would be. That's very scary to think about. Let's see this. Boiling point of iron. Oh my. Yeah, so you can see, right? Boiling point of water is just 100, very small, 100. Tapos ngayon, ang ating iron is what, like 3,000 degrees Celsius, right? And yeah, the thing now is that, here we go, crystalline. What do you mean crystalline? As in like mga diamond, ruby, or whatever. Crystalline is more general in this case. Very basically, it just means that you're arranging your atoms in a particular, a regular, parang manner. Let's say a lattice, right? And if you're going to look at the crystal structure, you're going to see, oh, it's just repeating. And you can actually remove, or kumbaga, you can determine its shape if you just know what we call a unit cell. Just like one copy of everything else, right? If I were to copy paste, right? And then I would propagate that to everywhere, makikita ko, okay, it's just the structure. It's just that times, I don't know how many times. Pag amorphous naman is somewhere in the middle, right? It has some structure, but not enough for us to say that it is crystalline. It is a bit more messy. And in this case, if we're thinking of glass, ito na, just to address that, glass is not crystalline a lot of the times. It is what we call an amorphous solid, right? Amorphous means that your atoms are arranged, yes, but not to a certain extent that you would call them crystalline, in the sense that, okay, they are repeating, right? Let's say, for example, this is the unit cell of this this formation, this crystal structure. This is your unit cell. And then honesty nga, you can even make an even smaller unit cell. You can see that this thing, if you copy paste it several times, you will create all of your structure. But for here, you can't find one agad-agad. Things are a bit more messy in this case, right? So that is amorphous versus crystalline, right? And now, okay, the thing about this is that metals are not confined. A lot of metals are not just confined to one particular crystalline structure. Usually, depende sa kung paano mo siya gagawin, kung paano mo siya i-manufacture, you will see different kinds of crystal structures. And this is not only true for metals, but also for something like ice. Right? Ice is a solid. And actually, kung nakita nyo kanina, the definition for crystalline comes from the root word crystallos, which refers to ice, right? If you remember, right, what snow looks like, it's crystalline in the sense that there is this repeating kind of structure, and depending on the pressure and the temperature that you're facing, mag-iiba rin yung itsura ng crystalline structure, mag-iiba rin yung itsura ng arrangements of the atoms in wherever you're seeing, right? And if we know that a certain material has different possible crystal structures, we would call it allotropic, from the words other manner. Sometimes it's also called polymorphic. Mas halata natin yung meaning kapag polymorphic, right? But basically, yes, this is solids with two or more possible crystalline structures. If you somehow manage to turn crystal structure A of this material into crystal structure B, that is what we call an allotropic transformation. Makes sense, right? And now, okay, ito na tayo. I researched somewhat for this. This was not in the book, but there are 14 possible crystalline structures. They are what we call Bravais lattices. Pero a lot of the things I've read make it clear that this is not specifically just for material science. This is for just, I don't know what you would call this, geometry ba? Right? Analytical geometry, something like this. But there are 14 possible structures, and only 4, or actually 3, are commonly seen in metals. Right? So I will show you all 14 just so you guys understand what I'm talking about. And ito nga, makikita nyo, they're kind of the same, right? Triclinic means that, well, it's a wonky kind of crystal structure. Nothing is the same, right? None of the 3 parang dimensions that you have here, A, B, and C, in alpha, beta, and gamma, have the same measure, right? But things start getting more clear kapag you go to monoclinic, orthorhombic, right? These kinds of things. And now, pupunta pa tayo dito, they become even more regular, right? As you can see in here, as you can see in here sa pinakababa, sa the cubic ones, right? You can see that A is equal to B is equal to C. So it is, or it does look like a cube, and in fact, alpha is beta, is gamma, they're all 90 degrees, right? You can also see in here the hexagonal one, right? The hexagonal one, very clear. A is equal to B, right? You can see nga that those guys are all parang the same dimension. And now it's very clear. It's very regular. Your gamma is 120 degrees, right? 120 for the, ano tayo ito? For the inclination. Inclination? No, but basta the measure here. Ito. This one. This is 120 degrees. Very regular. Kasi nga, pag tatlo mo na 120, pabalik ka lang ng 360. Right? Okay, that kind of thing. And now, i-highlight ko yung mga tatlo, 3 or 4, that are usually found. This is the first one, second one, third one, and fourth one. Actually, ito yung hindi masyadong nahanap. Right? This is the rare one. This is the rare bit. Right? And now we will spend some time trying to understand what they mean for our crystal structures, right? Let's first start off with the simplest one, the simple cubic, the one that's rare, right? It's abbreviated as SC, but basically, yun nga, simple cubic means that your atoms are found on the vertices of a cube. We have here what we call an atomic packing factor or packing density. What this basically means is that how much of your unit cell is occupied by an atom. And in this case, makikita nyo, ang baba, no? Parang 52% lang if you are thinking of a unit cell, and I will show it to you later, right? It only occupies 52% of that volume. So parang ang dami ko pa pwedeng malagay, eh. Right? And the number of nearest neighbors is 6, right? And ito yung itsura niya. right? This is what we call the unit cell. So you might be wondering, bakit parang kinat out mo? Kasi nga, ito yung nagre-repeat eh. Right? This is the structure that is repeating. If you copy paste this section and you put it over and over again, makikita nyo, it will create the sphere. Right? If it will create the sphere. Look at that. Right? Meron pa sa harap, meron pa isa sa likod, right? And look at this. How many nearest neighbors daw? 6. Kasi meron ka 1, 2, 3. Meron pa yung katabi, 4, 5, and then 6. 6 neighbors. Nearest neighbors. And makikita nyo nga dito in this drawing right here, although medyo kulang yung nasa loob, if we imagine this to be the unit cell, kulang. Nasaan yung nasa loob? Right? Parang ang dami ko pa pwedeng masiksik doon sa loob. And you would be correct because there is another kind of structure here, what we would call the body-centered cubic. As in, inside of the body, there is another atom. So not only are the atoms found at the vertices, meron na rin isa sa center and you would see the atomic packing factor go up. It's now 68%, about 70-ish percent. Right? And now its nearest neighbors are 8. Nearest. Ito ha. We're not talking about neighbors in general, but just the nearest ones. Ito na. Right? And this is where a lot of people struggle to like visualize. Like, what am I looking at in here? 8 ang nearest neighbors because if you're thinking of this atom right here in the center, the 1, 2, 3, 4, 5, 6, 7, 8. It has 8 nearest neighbors and very basically, yan, meron ng something sa loob. And mind you, all of their radii are the same. Huh? All of their radii are the same which means that syempre, hindi na magta-touch yung mga, yung mga atoms dito. But in this case, right, tumaas ang ating density still up to like 68%. Okay? I don't want you guys to go through all of the detail of like understanding why that number is the way that it is, although I would really like to. Kasi nga, this is more a terms subject. This is more a concepts subject more than it is a computations one. Although I would like to make it very computations based, but here we are. Okay, and now we will have another one. What if instead of the extra atoms being inside of the cube, what if now they're in the centers of the face? Face-centered cubic, FCC. Kanina yung body-centered cubic is the BCC. That will be atoms found in the vertices and in the middles of the faces of the cubes. Right? Now, the atomic packing factor here, you would see is at an all-time high kasi ang dami nyo ng mga atoms. Right? 74.05%. And now, the nearest neighbors, 12 na. Dumami na. Right? So, you might be wondering, oh my gosh, how am I going to count this many? Right? And I'm gonna struggle and try to show you guys how this can be done. I mean, there is something on the internet din naman, but you can see, right? Each face has half of has half of an atom, right? And these atoms again, like they're not as easy as just saying like, oh, it's just a sphere. Right? It's more complicated than that, but to simplify things for now, this is the FCC, face-centered cubic. So you might be wondering, nasaan na yung mga nearest neighbors nila? Right? So in here, you will have, let's say for example, ito yung titingnan natin. Meron kang 1, right? Meron kang 2, meron kang 3, meron kang 4, meron kang 5, and then meron kang 6. The one in the back and the one in the front. And then you will have 7, the one on the face in here. Number 8, nandito. Number 9, nandito. Number 10, nandito. Number 11, nandito. Okay, I'm gonna have to draw other faces for this to work properly. You know what? Let's just make it here. Okay. You'll have this one, and then I will have this red one right here, and I will have this blue one on top, and I will have this green one in here. Mukha tuloy akong geometry ngayon. And then I'll have this yellow one in front. Ganyan. And then, I will populate. Right? Ito ang ating tinitingnang atom. Right? And isipin na lang natin where all of the other stuff is. Okay? Hopefully, we will have 1 neighbor, 2 neighbors, 3 neighbors, 4 neighbors, 5 neighbors, 6 neighbors. Hopefully, that makes sense. Right? Yun lang yung pinaka malalapit niyang kasama. And now let's think of the faces that each one has. Meron ka ba dito magiging 6 na yan? Okay, 6 na. 6. And then 7. Makikita natin yun in between the faces here. There's another one here, 8. There's another one here, 9. There's another one here, 10. There's another one here, 11. And there's another one here, 12. Right? Kaya 12 ang kanyang, ano tawag dito? Nearest neighbors number. Right? 12. Okay? Okay. Anyway. Ba't parang hindi siya same? Pero okay. Now, there's another one which we call hexagonal close packed, and actually, right, just so we understand, this is also what we call cubic close packed, the CCP. Anyway, punta na tayo dito, hexagonal close packed, and HCP ang tawag sa kanya. And it's a bit difficult to show you guys or just to tell you what hexagonal close packed is just based on words, so you're gonna have to see it for yourself, right? Pero in this case, just think of how best you can pack things in a triangular or in a hexagonal manner, right? So, the atomic packing factor for this is 74.05, kind of familiar because it is the same, right? Same na same siya sa atomic packing factor ng ating FCC, right? And because of that, the number of nearest neighbors is also 12. Dito mas madali makita kung bakit 12 ang kanyang nearest neighbors is because if you imagine another kind of like a unit cell on top, right? If you imagine another kind of unit cell on top, meron ka pa ditong tatlo in the middle here. And now, if we're going to point out where the nearest neighbors are going to be, edi ito, we will take into account this guy. We will have 1, 2, 3, 4, 5, 6. Meron pa siyang tatlo sa baba na pinakamalapit. 1, 2, 3. And meron pa siyang tatlong pinakamalapit sa taas. 1, 2, 3. So 6 plus 3 plus 3. That will be 12. Right? Yun yung kanyang nearest neighbors. Okay? So yun. Okay. So hopefully, if hindi nyo pa rin gets, I'm so sorry. The thing about this is that I can just take you to so many possibilities here, right? To so many possibilities here, and you can even make the distinction nga na there should be dapat hindi ito counted, right? Dapat hindi ito counted, right? And what you should just look at are the different faces that are possible. Yun galing ang 12. I think that's the better answer for this. Kasi meron pa dito na face dito. Meron pa dito na face dito. Kaso ma-drawing ng maayos. There's another one here. Right? And then there's another one here. Yung face dito. But then again, it's gonna look so cluttered, right? So cluttered, and you're going to see, right, different parang ways naman in the internet. Number of nearest neighbors, FCC. Yes, I'm aware. Yan, oo nga. So it's just going to be in the faces of each, right? Next. Yes, the next nearest neighbors, next nearest. Okay, you know what? Yun. Right? Those are the nearest neighbors for the face-centered cubic. Oh, for them, they took it as yung sa isang face. Okay, let's try that one out. Let's veer away from this. Let's try this. Oops. This is our original, and then this is our kasama. Ayan, may kasama tayo dito. Ito, ganyan. We will have our face in here. Makikita natin we will have 1, 2, 3, 4. Okay, so those are 4. 1, 2, 3, 4. And then, meron pa tayong, what else? We will have one face here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if you guys were a bit confused as to where I was putting all of the dots, imagine na lang like a die, like a die, pero instead of 1, 2, 3, 4, 5, 6 as being the faces, it's all just ones. Right? Puro ones lang siya. 1, 1, 1, 1, 1, 1. Right? And we are, kumbaga, we are putting these two dice, right? And then we are just counting which parang vertex and which one or which atom in here, right, it's closest to. So ganun ang kanilang example and here as to why the number of nearest neighbors of an FCC is 12. So very slicey and dicey ito. Right? And I'm using that word very purposefully because we'll talk about how these things have their weaknesses, right? But if you want, right, and i-upload ko rin naman yung files natin for this, right? Here is a good parang representation of the different cubic, basta crystal structures, right? You'll see here nearest neighbors, right? Packing efficiency, ayun, that's another thing to think about. Right, to call these things, right? Body-centered cubics, you'll have here different metals. It can, it can manifest as, so iron, chromium, for BCC, ito, iron, chromium, manganese, CB, you might think to yourself, there's no CB, and yes, wala na nga CB, it's replaced by NB, niobium. It used to be columbium. And we have tungsten, tantalum, titanium, vanadium, sodium, and potassium. For FCC, we have, again, iron. So, ibig sabihin, iron is allotropic. Diba? It has two different possible crystal structures. Iron, aluminum, copper, nickel, calcium, gold, silver, lead, and platinum. And then for HCP, these are a bit weird, right? And makikita nyo later, beryllium, cadmium, magnesium, zinc, and zirconium. Right? And ito na nga yung sinasabi natin. Dapat nga 3 lang talaga. Pero I was thinking, surely there must be a metal that crystallizes into simple cubic, and there is. It's polonium, PO. Yan lang. And BCC metals here, because of the way that their crystals or their atoms are organized, they're going to be strong, as in they're going to resist being moved, right? And because, ito na nga, makikita natin to later, I'll expound after this, FCCs are ductile. Right? So you might be thinking, okay, why is that ductile? We'll talk about that later. And then HCP, why are they brittle? Nakalagay daw dito, HCP metals are not ductile. So, why is that? Why would that be the case? That is because of this. Crystal structures, as you might think, okay, they're repeating. So you might think to yourself, oh, that's great, right? But the thing is, because they are repeating, their structure is predictable. And if you can somehow direct your force through any of these points, or not just points, but planes, you will deform these crystal structures. These planes are what we call slip planes, right? These are basically planes where slip can happen, right? These are planes where slip basically happens very easily. So slip as in like literally you slip, right? You slide or you shear past each other, yung layers natin, right? And in this case, this is what determines the properties for these crystal structures, right? Here we have the 3 that are usually found in metals, and kung ano man Right? Kung ano man yung naka-highlight dito, nakikita natin yung mga slip planes ng BCC, ng FCC, and ng HCP. Right? And now you will have here, excuse me. Okay. Anyway. Right, now you will have here, makikita nyo, these are planes wherein you will see the most amount, or the highest amount of molecules. So if you think about it, right, for BCC, there's 6 possible parang planes where you can just slide past along each molecule. Right? For FCC, you will have 4 planes, right? You will have 1, 2, 3, 4 possible configurations where you can shear past them. And for HCP naman, you will only have 2 slip planes, right? Or just 1 nga eh. Actually, these guys are just repeating, right? Guys are just repeating. And so now, this is why these metals have these kinds of properties, right? Isipin na muna natin yung HCP. It has 1 slip plane. So you might be thinking, isn't that good? Right? Good in here is kind of not the correct term because you might be using HCP metals or you might just be using HCP materials for different applications. In this case, HCP has only 1 slip plane. So you might be thinking, that's very resistant to deformation. Yes, but again, the trade-off. Right? If hindi siya marunong or if it does not easily deform, then it means that at some point, if you give it enough force, it will just crack. It will just break. It's brittle. Right? But for these other metals that have BCC or FCC, they are more susceptible to small deformations. And as a result, small deformation lang, I can maybe just slide just a little bit more. Maybe I can deform just a little bit more, and that kind of continuous deformation, okay, that's a different thing. Those kinds of small deformations are what allows metals to be ductile, right? So ganun ang ating reasoning here. And just to parang crystallize things, just to crystallize the definition, this is what we mean by a dislocation. Right? When you have a dislocation, it's just a small disruption or small error in the crystal structure. Right? But this is where usually these faults begin to happen. Here we have 2 different kinds of dislocation. An edge dislocation, as you can see, may extra dayo dito. Dapat wala to eh. For this to be a good crystal structure, for this to be a very predictable crystal structure, this extra layer here should not be present. Right? So it's like an edge cutting, right? It's a cutting edge. If you were to think, this is like a knife that is cutting through this crystal structure. Yes. And this one naman, this is the screw dislocation. And you might be thinking, it's just parang nausog lang yung isang layer. Yes. Yes. And if you think about it, if it's going to go through all the way, if it's going to screw just a bit more, if it's going to twist a bit more, it will look like it's being dislocated like this. Right? That is our definition of a screw dislocation. Right? Okay. Now, hindi lang yun ang ating mga defects. Right? Sabihin na lang natin, hindi lang yun ang ating mga defects. In this case, what you can also have are others, right? Other really smaller disruptions in your crystal structure. And they can be one of 3, a vacancy, an interstitial, or a substitutional atom. Right? Very easy to just spot. A vacancy is kapag wala. Right? An interstitial, ibig sabihin ng interstice is somewhere in between. So, if just another atom were to be in between, because, nothing is perfect. Right? Meron dyan na lalabas na, meron tayong extra, or I got picked up by something, there's another extra atom in there. Pwede yun. And if the material properties are right, and if the bonding is correct, what you can have is, instead of this metal being in this crystal structure, you'll have a substitutional, right? I don't know if you guys are like clued in into this, but a lot of people, there's a sizable amount of people who think that if they were aliens, they would not be made out of carbon, they would be made out of silicon. And a lot of people say that because magkakapareho sila ng parang material property. You know what? Let's go to the table. There you go. Yeah, look at them. Carbon and silicon, magka-group sila. They both have 4 valence electrons and they can be substitutes of each other. Right? If you're gonna have a crystal structure of carbon, silicon can fit right in there. Right? Depende na lang if it's bigger or smaller, mag-iiba yung itsura na magiging crystal structure nyo. And here, dahil mas malaki siya, well, the crystal structure should give way, sabihin na lang natin, or it should deform to accommodate this different metal. Right? And so now, ito na. Right? Sabi natin earlier, a material may have more than one type of crystal structure. What I'm saying here is that it can have more than one it can have more than one crystal structure in the same structure. Kumbaga, in iron, it can be either BCC, FCC, or both in the same, kumbaga, sheet of metal. Right? This sheet of metal can be BCC, purely FCC, but more than what happens more often is that there's a mix of these crystal structures. You might be wondering how do they mix, right? And even if, right? Just so we understand, this is what we call a polycrystalline structure. Ibig sabihin, there are many kinds of crystal structures within the material, but even then, right? Even if isa lang yung crystal structure natin, like purely BCC, you would not expect the material to just be one sheet of the consistent crystal structure. It has multiple orientations. As in, for example, at this point, nakaganyan yung orientation ng, I can't see myself. Nakaganyan yung itsura ng ating crystals, but for this region, baka nakaganyan siya. Right? And that will occur on and on and on, and this is the time that we should go to grain structure. Right? Nothing is perfect. And in this case, this is the kind of imperfection that lends itself to strength. We'll talk about that more in topic 5, but in this case, okay, kung maraming mga maliliit na crystal structure that have different orientations, they are what we call grains. Right? They are what we call grains. So in this case, right, you can't see them in the naked eye. They're that small. Pero if you look closely, if you treat it with chemicals to, kumbaga, remove anything that will hinder or impede good vision, makikita nyo yan in Damascus steel, right? If you guys know that thing, makikita nyo yung, kumbaga, yung iba't ibang what do you call this? Damascus steel. Makikita nyo yung iba't ibang mga metals in here. Yeah, look at that. Wow. Right? You will see the different kinds of, hindi nga to grains eh. Basta these are just layers, but they are close enough because you can see very clearly where the iron is, where the carbon is. We'll talk about that later. But yeah, right? And this is how they usually happen. When molten metal, right? When molten metal starts off, of course, everything is liquid. Medyo nag-jiggle pa sila because they are in the state of a liquid. And now, this is what happens. When they start to solidify, they're what we call nucleation points. These points are just sometimes other defects. Minsan in your iron, meron kang mix na may carbon or whatever, blah, blah, blah. There are these points where nucleation begins and grains start to form inward. So, palabas sila yan. Palabas. Right? Ganyan ang magiging itsura ng grain growth. And what happens is that there are going to be, once they form, there are going to be these grain boundaries where hindi na same ang magiging orientation. That's why they stop. Right? That's why they stop. Kumbaga, ganyan na yung magiging orientation, and as a result, right? As a result, they will have kumbaga boundaries in here set in place. Right? And yeah, yan itsura ng mga grains natin. As you can see, the scale is very small. 100 microns, that is what, like 1 times 10 raised to negative 4? Yeah, it's very small. 100 times 10 raised to negative 6. Maliit nga lang talaga. Right? What is even a millimeter? I forget how small that is. So, yeah. This is what happens if you chemically treat it. What usually you need to do is you need to submerge it in a chemical that attacks the materials in the grain boundaries. Ang nangyayari, nagdi-dissolve sila, nakikita nyo talaga yung mga grains. Although there are some bigger grains out there that you can see. Grains, crystal grains, copper. Oh my goodness, look at those grains. Wow. So, ayan, mga grain boundaries. There you go. You can search for these things and, oh my goodness. Sige, balik tayo. Grain structure na lang. Grain, copper, grain structure. Oh my goodness, look at them. Okay, enough. Wow. Okay. Anyway, ayan. Now, ito ang ating dalawang controls when it comes to grain formation, right? If you have more sites for nucleation, right? And you can control for that using by adding different chemicals, ganyan, right? Those create smaller grains. And how you control growth rate, as in depending on the temperature, yung pagbaba ng temperature, yung pag-solidify, maybe if you do it slower, right? Something else will happen to the growth rate. That means that if mas mabilis mag-grow ang iyong mga crystals, you will have bigger grains, of course, right? And in this case, if you want a metal to be strong, you want it to have smaller grains. Sabihin na lang natin, right? Because these smaller grains are basically, if you imagine, right? If you imagine soil or sand, they have really small grains, and what happens is that if you pack them, they become very strong. They become resistant to parang how should I say this? They become resistant to deformation. But if it's like big rocks, you can very just easily move the rocks away, right? You can easily shake the small rocks. So we're talking here very small grains versus very big grains. You want smaller grains, and this is why meron tayong tinatawag na ASTM grain size number, right? These are basta makikita nyo lang, right? You will have here the ASTM grain size number is the small n, is basically the number of grains per square inch of material. So if you're going to magnify it 100 times, you're going to take a square inch, you're going to count how many grains there are in there, you plug that into ng, number of grains, then you're going to put it in the grain size number formula. Makikita nyo that it's a logarithmic scale, because if you think about it, you're going to count a lot of grains, right? You're going to count a lot of grains. So, ayan. Now, medyo topic 5 pa ito, but this is good enough for us to discuss here, right? This is good enough for us to discuss here. So, saan ba nagde-depend ang mga properties, ang mga performance ng bagay-bagay, right? Very basically, the type of crystal structure. If it's BCC, FCC, HCP, simple cubic, right? That determines a lot of it, but also the kinds of atomic bonds it has. Sabi natin kanina, right? Ionic bonds are very strong. They're very parang what do you call this? They're secure, they're stable, right? Metallic bonds, they have seas of electrons. Edi yun, mga properties. Right? The spacing, baka naman mamaya malalaki yung mga spacing natin. So ibig sabihin, these guys have lower density, mga ganong klaseng bagay, right? Because they are spaced farther apart. And number 4, yun nga, density, right? Okay. Right? And so now, we'll move on to something a bit different this time around. But now, yung kanina sinasabi ko, right, is that multiple metals, basta multiple materials may participate in the same crystalline structure. They might replace, right? They might replace kung ano man yung totoo or dapat na main or primary metal or material in that crystal structure. They may be in the middle of these crystal structures, and this is what we basically call an alloy. Right? An alloy is coming from the French alloyer. Wow. Very fancy. Which basically means it's a metal wherein may paghahalo tayo between a main element and an alloying element. Right? The most basic example of this would be steel. Steel, you might think, is an element, but no, it's actually iron plus an alloying element, which is, you wouldn't even call it right? You wouldn't even call it what do you call this? You wouldn't even call it a metal. It's carbon, right? You add a bit of carbon into your steel. Oh, sorry, into your into your iron. You create steel, right? The amount of carbon is what depends is what determines how hard it is, how brittle it is, how ductile it is. Pero yun, right? If we think about it, almost everything, right? Almost everything that we touch has been in contact with some steel or some iron, and our modern life depends on these alloys, right? So yun, right? They're usually there to add or to enhance or to just modify the properties of something, right? Ayun, sinasabi na natin steel. If you're thinking of stainless steel, you're gonna add to steel some chromium, right? And sometimes some molybdenum as well, right? You'll see that in the industry more, right? And then you'll have bronze and brass, right? So medyo nakakabaligtad sila because bronze is copper and tin, but brass is copper and zinc. So parang nabaligtad kasi the what do you call this? The chemical symbols for tin and zinc are SN and ZN, pero yung S napunta sa Z, yung Z napunta sa S, right? So yun lang, share ko lang. And the more how am I going to say this? The other kinds of alloys you might know, amalgams, right? The things that people or that dentists use to put in teeth, right? They're mercury. They're mercury plus other metals, and the thing that's good with mercury is that at room temperature it's liquid. So that's one of the few metals that does that, right? And solder, right? Solder, right? Panghinang, right? Our solder comes from lead and tin, right? If you combine those together, it doesn't take a high temperature for them to melt, right? That's the kind of enhancement, that's the kind of modification that we want, right? Rose gold, very surprising. It's just gold and copper. That's where you get the kind of reddish tinge of rose gold. And sterling silver, you might know this as well, just like off by name. It's silver and copper. So it's very cool. Electrum, were the alloy shout out. Electrum is gold and silver. That's pretty cool. So yun lang. Share ko lang. And I suppose if you're thinking of alloying as just combining different materials, metals together, right? Yun na yung pwede pa nating stretch yung definition niya eh. Right? We'll talk about that later. But for alloying, you can just have metals that are insoluble. There's an alloy here that's bismuth and cadmium. So if i-combine mo, hindi talaga sila mag-combine in the sense that like they're going to what do you call this? They're going to experience a mixing. They're just like water and oil. They're in the same alloy, but they're not mixing, right? So, metals may exhibit some kind of solubility as well, right? Some kind of solubility as in, well, a lot of the metals that we have currently, and sometimes, a lot of the different alloys that we have currently, they exhibit some kind of solubility, as in like it will create a homogeneous mass, right? A homogeneous phase. And sometimes they are so good that they just form intermetallic bonds. Sometimes this element A usually just bonds with its other element, right? It's same element pala. Kumbaga, this is what happens in metallic bonds. But in alloying, it might happen sometimes that it may bond with another, with the alloying element itself, right? And then in this case, yun nga sinasabi natin earlier, alloying elements may either replace, substitutional, or be in between the crystal structure. This is the interstitial, right? And this is important because if we're going to stretch, if we're going to generalize the definition of alloying, you might think of, wait a second, if you guys are interested in electronics, you might have heard of doping, right? Not doping as in like the parang the addition of illegal substances to like enhance performance, but doping as in semiconductors, right? This is adding impurities or adding alloying elements, quote unquote, to a semiconductor to improve its electrical conductivity. Either you add something in there because you know that on its own, the semiconductor is not very good at its job of like being selectively conductive, right? So you're adding doping materials like ano bang tawag doon? Germanium sometimes, right? You guys have probably seen this gallium arsenide, GAS, right? Those kinds of materials are added to what is that, silicon, right? Para ma-improve ang kanyang electrical capabilities, electrical properties, right? And okay, last part. We're in the home stretch ngayon. We're going to talk about this, and this should be a transition into your next lesson, right? Your next topic, which is about mechanical or just material properties, right? Right now, we're talking about structure, but now, ito na yung ating link. Because these structures, right? These structures are going to determine the properties. And now, in the next lesson, we'll talk about how the words hard, stiff, rigid, ano pa ba, strong, are all different in the field of material science, even though like in normal jargon, in normal vocabulary, they're the same, right? But ito na yung ating link, right? What are these materials in the manufacturing world? What are these materials used for? It's to support things, right? And when you're supporting, you are being loaded with forces, kumbaga, right? And when forces are applied to a material, it may react differently depending on the amount of applied force. Makes sense. We've lived enough on this earth for us to know that, that makes sense, right? And so, I don't remember if kayo yung may eng-match na subject. I think you guys have mentioned it once or twice na meron kayo. So, babalik ko lang. Stress is denoted by the letter sigma, small letter s in Greek, right? This is what we mean when we say force over area. Pero you might be thinking, wait a second, that's also pressure. Stress is different because, diba, pressure is external, right? Peer pressure is the pressure from your peers to do something that you don't want to do, right? But stress is something that someone is not giving you. It's something that you are experiencing by yourself, right? Someone might be giving you a hard situation and you are the one feeling the stress from that hard situation, right? Is force over area. Right? And on the other hand, we have strain, right? Strain is how you respond to the stress. Ito usually when you're stressing something, now we're no longer anthropomorphizing things. When you're stressing something, you will see later in the presentation I've made, right? Your length or basta your dimensions will change accordingly. Depending on the material itself, it will change accordingly. And very basically, this is denoted by the Greek letter epsilon, letter E-ish, right? This is the change in the length over the original length. So, ibig sabihin, if your strain is positive, humaba ka. If your strain is negative, lumiit ka, right? And the stress-strain diagram is a very important diagram in the field of material science where your stress is the y-axis, your strain is the x-axis, and basically this is how you would visually represent kung anong nangyayari sa material if it undergoes any stress, right? If you undergo stress, you will exhibit strain. That is the rule here, right? And now, you'll have here a wall, you'll have here a rod, and I will have here a force. And for us just to see, kumbaga, the response of this rod, I don't know what material this is. Let's just say, I don't know, for example, it's steel. Sabihin na natin, right? This is specifically for ductile metals. This is for ductile materials. If we're going to give this a force, look at what happens to the stress strain diagram, right? It will go down. Kasi nga, binibigyan mo siya ng compressive stress. If you remember from our Engmech, right? Compression means negative, right? And because lumiit yung ating rod, look at what happens, right? Lumiit yung ating rod, it will get negative strain. And if hinila mo naman yung rod, you will now have positive stress and positive strain. When a material is pushed, it compresses. When a material is pulled, it stretches. And in this case, right, your modulus of elasticity is the slope. Makikita nyo kanina is that these are just lines, right? And this is the slope, right? Rise over run, y over x, stress over strain, right? So in this case, when the force is removed, makikita nyo that the material returns to its original shape, right? So in this case, this is what we call elastic deformation. Elastic is in like a rubber band. If you pull it, if you push it, if you let go, it will return into its original shape. Elastic, right? And then ngayon, let's think about it this way. Yung secondary effect, just look at the shape of the rod. Not the length of the rod, but the shape of the rod. If you push on it, but nag-bulge. Interesting. If you pull on it, it gets thinner. Right? It makes sense. Yun nga, it makes sense naman, especially if you do it with something that is less stiff or something that is less elastic. Let's say, for example, rubber or marshmallow. Yeah. Right? You will see this much more pronounced effect. This is defined by Poisson's ratio. This is by Simeon Denis Poisson. And this is basically kung gaano ka-stretch yung lateral dimensions mo when you stretch it in the longitudinal dimension. Right? If you're gonna push on something, it will bulge. If you're gonna pull on something, it will get thinner. Right? That is Poisson's ratio, or that is Poisson effect in action, and it is It is described by Poisson's ratio, right? Pag mas malaki ang Poisson's ratio, ibig sabihin mas pronounced ang pagbabago in your lateral dimensions. Like if you push on it, it will really bulge. If maliit ang Poisson's ratio mo, and there's some materials where Poisson's ratio is 0, ang nangyayari lang kapag Poisson's ratio is 0 is that this is your original. This is your original. And ang mangyayari is instead of, for example, if you push it, ang expectation natin ay lalaki siya, di ba? Lalaki siya. And it will get compressed. If you push it, no, it just stays the same parang dimension. This is cork, I think. Cork has Poisson's ratio of 0. Poisson's ratio of cork. Yes. Okay. Ayan pala, ayan, mga ating mga values here. Don't be scared about these things. I will not be including this. Rubber's 0.5, very high. Ayan, cork, 0. Right? So, ibig sabihin talaga pag rubber, if you're gonna stretch rubber, of course, it's going to change very drastically. Right? Yeah. Yun lang. Poisson's ratio. Now, I will have here a reference material, yung hindi mo sinastretch, because now you will see the force arrow is much bigger this time around. If we pull, it will go elastic, yes. If you let go right now, okay pa yan. It will still return to its original shape. But if you stretch it just a little bit further, Now, if you let go, it will no longer return to its original shape, right? After a certain point, the material no longer returns to its original shape. This is what we call plastic deformation, right? This is what usually happens to plastics. When you rip plastic, it will not magically deform back into its original position, right? Yun. And if we take this all the way with large forces, you stretch it, it become elastic. If you let go right now, kaya pa yan bumalik sa original niya. But if you stretch it just a bit more, it will become plastic. And if you stretch it just even more, it will then start to neck, right? This is what we call necking, right? After a certain point, the material starts necking, right? You will see here, there's a drastic change in your diameter. And then, at some point, of course, ano bang expect natin, right? It will fracture. It will break, right? So, just one more time, right? It goes from elastic, right? Elastic to plastic. And then at some point, after it reaches the highest stress that it can, sabi niya, you know what? No, thank you. I will now dip out, right? Ayun na, it will break, of course, right? And this is the usual kind of image that we see in stress strain diagrams. There's a point where it's linear. That is what we call the elastic region or the proportional region. And at some point, it will get an increase pa, just a little bit more, up until it reaches this point right here. This is what we call the tensile strength. Ito na yung highest na kaya niya. And after that, well, it starts necking. Ito na yung necking period natin. Ito yung necking region natin. And then at some point, boom. Right? It fractures. Yun ang ating ultimate strength. Okay? Okay. Yun lang. Right? And you might be wondering, sino or what determines what kind of deformation is available? Kasi some of it, right? Some of the materials that are possible, at some point they just break. Right? Ang sabi natin kanina, this is for a ductile metal. This is for a ductile material. For brittle materials, bakit wala nang stretching? You don't see concrete stretching, right? It just, boom, it breaks, right? And the answer to that is how it has to do with absorbing and redistributing energy, right? If you're going to see here, this is a kind of a 2D, right? 2D representation ng ating what do you call this? Crystal structure. And basically, you will see in here that there are weak points. There are weak points in here. You can see if you're going to stretch this, ang mangyayari is that it will receive energy, right? And medyo komplikado if I try to explain where the energy comes from, but basically sinistretch mo eh. Right? You're giving it energy. And what it wants is to stretch back, is to snap back to its original position. But what happens is that at some point, if you give it too much energy, depending on the kind of crystal structure that it has, sasabihin niya, okay, kaya ko pang bumalik sa original kong position. But at some point, right? At some point, they're going to be like, okay, you know what? The best course of action for me to not fail is to just deform, right? This is the slip plane we are talking about earlier. And at some point, if you stretch it past this certain amount, it will deform, and ang mangyayari, you will see these dislocations happen, right? Dati, 4 yung atoms na nandito sa taas, but now it got pulled down to the second, right? To the second layer. And now, if you put it back, if you remove the force, what will happen is that nasabi nila, you know what, this is good. Okay na to. Pwede na to. Right? And the plastic deformation is there. Right? As you can see, this is the original, and now medyo mas mahaba na siya ng konti. Right? So that is the reason why, right? Depende na nga siya sa kung ductile or brittle. Sabi natin kanina, kapag brittle, yes, it only has one slip plane. Pero, kung hindi siya magsislip, it's much more probable that at some point, if it receives enough energy, it will be like, you know what, sige, magtanggalin na lang natin yung mga atomic bonds natin here because everything in here has bonds, right? And at some point, if it receives too much energy, it will be like, you know what, sige, let's just split, right? And now that is what when fracture occurs, right? Whew. We're almost done, right? And then ito, you might think this thing is a kind of a medyo counterintuitive, but most metals actually become stronger, or rather they can handle things better, they can handle forces better if they are plastically deformed a little bit. So you might be wondering, paano nangyari? This is what we call strain hardening. This is done very usually in the industry. When you have something that you have manufactured, like a metal, usually if you want it to be stronger, you just stretch it just a little bit more and then let go. And then stretch it a little bit more and then you let go. And why are we doing this? This is because we want to induce plastic deformation. And ibig sabihin kasi pag na-plastically deform, you will create longer grains. Right? So if you think about it, okay, ano naman ang mangyayari kung if I go from here, right? If these are my grains, if I stretch them, they will become like this, and this. Right? Ano naman? Right? These grains, because you keep stretching them, they're going to get tangled. Right? And if we're thinking about it, where do fractures come from? The weakest points in your crystal structure is the boundary, right? This is why if they crack, if concrete cracks, it's like this, right? Hindi siya parang, hindi siya ganyan, right? It will find the grain boundaries of the different parang materials inside the concrete. And if these grains have these tangles, it will be much harder to find clear-cut lines where you can induce your failure. So at this point, kapag mas tangled yung mga grains, right? Much like before, if we're thinking of grains of sand, smaller grains being tougher, being more able to withstand these forces, if they are tangled, hindi mo sila basta-bastang untangle. Hindi mo sila basta-bastang pwedeng makalas because they are now tangled together. Right? That is the technique behind strain hardening. So this is what happens, right? You see this, medyo elastic pa siya and then it becomes plastic. And then you let go. Right? You let go, it goes here. And then it's now deformed. Ayan, makikita nyo may strain na siya agad-agad. Even without stress, right? Even at zero stress, it now has some strain. And then you do it again. Sige, you load and then it becomes plastic. And then you let go. Okay. Nandito na siya. It even has more strain now. Parang pinapahaba mo talaga yung iyong metal without breaking the metal. And what happens is that, look, it can only handle this force kanina, but now it can handle much higher stresses now. In essence, you're making this thing stronger. Ano yun? What doesn't kill you makes you stronger? Ha ha ha. Right? You're making it stronger by deforming it plastically. Okay? And another way, hindi pa pala. Sorry. If we're going to think about this now, it's going to be stronger in one direction. Hindi mo siya pwedeng maganyan-ganyan lang, but it's going to be kumbaga its material properties will be different based on another kind of direction, right? This is why we have these two adjectives here called isotropic and anisotropic, right? Ibig sabihin kapag isotropic, iso meaning same and tropos meaning value, all of your properties are uniform in all directions. This is what happens when you have small grains that are parang uniformly sized, right? Ibig sabihin, no matter if you deform them here or whatever have you, they will respond the same way. But if it's anisotropic, an meaning not, right? Ibig sabihin, well, they're not uniform in all directions. Let's think about this in terms of wood, let's say, for example. Wood is a fantastic example of an anisotropic material, right? It has fibers that run like this. So, anong gagawin natin? If you want to split wood very easily, just take an axe and chop it down the middle. Wag mo i-chop like this. My goodness, you're going against the grain. Like, for example, steak, sabihin na lang natin. Ay, basta any meat in general. You'll find that it is easier to cut along the grain than against the grain. Right? So yun lang. Isotropy and anisotropy. Right? And ito na yung sinasabi natin, right? There's another way to change or to kumbaga to deform, to modify the grain structure or the crystal structure of your material, and this is recrystallization. Hopefully this is still familiar to you guys because napag-usapan na natin to before, right? This is a phenomenon where even if you don't melt the metal, you will have a chance to reorganize, to reform the crystals, to reform the crystals at not boiling temperature, not at melting temperature, but at recrystallization temperature. And what usually happens is something like this, right? You heat it up, you heat, and you will see, you'll see at the beginning, ang daming maliliit na grains. And so what happens here is that recrystallization may be good at forming these small grains, but look, if you continue heating, big grains bad, right? And that's because if you continue doing this again and again and again, ang mangyayari is that you're just melting it at this point, right? Recrystallization needs to stop at a certain point when you're happy with the amount and the size of your crystal grains, right? So yun. You'll see here. Let's just let this GIF play just a little bit more. It's so cool. Look at that, right? Pero yun, this is again just to remind you guys what happens in cold versus hot working, right? When you're hot working, you're trying to recrystallize, right, your grains. Para ang mangyari is mas maliit, mas lumiit ang ating mga grains so that it's more ductile, it's stronger, it's less strong but it's more ductile. And in cold working, you are taking advantage of strain hardening. Ang nangyayari, you're not recrystallizing, but in this case, you're just trying to deform the grain structure, the crystal structure that is already present, so that you achieve strain hardening, so that you can have improved strength at the cost of now it's less ductile, right? And again, anyway, anything in between is called warm working. So yun lang naman. And in this case now, because I've told you guys the requisite information that you guys need to know, you will now be equipped for topic 5 when we're going to, kumbaga, quantify, right? Kasi right now, we're trying to qualify what's happening. And now, the numbers, right? Yun yung ating topic 5. How will we denote how good, how strong something is, how rigid, how elastic, blah, 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 blah. That will all be in topic 5. So yun, how long did this run for? 1 hour 43. Okay, sounds good. Ayun, I hope you guys enjoyed this. If you needed the time, you could pause, of course, to collect your thoughts, have a think at some of the points in here, and there you go. Right, that is topic 4. Thank you very much for listening. I will see you soon for topic 5, which is going to be material properties na tayo. Okay, thank you very much.